So in the last several lessons, we've been introduced to the idea of acids and bases, and in particular to the Bronsted-Lowry definition of an acid. So you know at the basic level of a reaction that an acid is a molecule that donates a proton during its reaction. We've also talked a lot quantitatively about acid-base chemistry. How strong is an acid relative to another acid? How acidic is a solution relative to another solution, using the ideas of pKa and pH, so acidity constants and the pH scale. What I'd like to do in this last lesson is to pull those two different ideas together to talk about how acid strength, this quantitative measure that we've been talking about, is connected back to things that you learned in the early part of this course. That is molecular structure and bonding. So how can we use the information that we know about the basic chemistry of how atoms form bonds to predict whether or not something will be acidic and how acidic it will be? So let's get started. The first thing you have to remember is that Bronsted-Lowry acidity is the ability to donate a proton. So we can depict any Bronsted-Lowry acid generically just as a hydrogen atom attached to the rest of the acid that I've abbreviated here as A. So you can think of that line between the hydrogen atom and the acid as representing the bond between the hydrogen and a particular generic element, or in the case that it's a larger acid, the rest of the acid. So if we think of a couple of examples, HCl, hydrochloric acid, and HBr, hydrobromic acid, are both Bronsted-Lowry acids with a single bond between the hydrogen and the halogen atoms. And our goal in this lesson is to connect our understanding of the bonding between the hydrogen and the heteroatom to the idea of acidity. What aspects of bonding lead to the likelihood that something will behave like an acid? So the first thing that you want to remember is that a strong acid is one that donates its proton easily. So let's think for a moment about the reaction of a Bronsted-Lowry acid. It generates a proton and the conjugate base. The bond is cleaved such that both electrons end up with the conjugate base, generating a proton. So it's not that one electron goes towards the hydrogen and the other towards A, but rather both electrons move towards A, and hydrogen just loses out. And that's why we're always talking about acids as being proton donors, because this is a reaction in which the hydrogen atom is losing its stake in both electrons to generate simply the hydrogen nucleus, the proton. So that means an acid is one in which the HA bond is relatively easily cleaved, but it's cleaved in an asymmetric way. It's cleaved such that the electrons remain exclusively with the A, not with the H. So from the perspective of molecular structure and bonding, there are two main factors that you can think of as being associated with acid strength. That is the strength of the bond, because in the course of an acidic reaction, that bond has to break, and the bond polarity. You'll remember in the next few moments that bond polarity is a measure of how uneven the distribution of electrons is between two atoms in a bond. So let's look at each of these two factors in turn. I think the first one is a little bit easier to intuitively see the relationship between it and acidity. So let's look at a sort of concrete problem. The question is, do you expect a strong or a weak HA bond to lead to a strong acid? So again, the acidic reaction of HA is cleavage of that HA bond such that the electrons go entirely to the A species and you generate a proton. So that means weaker bonds are more acidic. If that bond is easier to cleave, it's going to be easier to create that proton species. So a weak HA bond corresponds to a stronger acid. And we can use that idea immediately to be able to compare the strengths of acids, or predict the strengths of acids, based on the energies of the H to heteroatom bonds. So let's take a look at this second problem. This problem asks us to use the strengths of H heteroatom bonds to rank the relative acidity of a collection of halogen-based acids. So you see in this table the bond energies associated with a hydrogen to fluorine bond, a hydrogen to chlorine bond, and a hydrogen to bromine bond. And what you see is the HF bond is strongest. Highest energy corresponds to the strongest bond. That's the energy you would have to put into the system in order to break that bond. And acidity, we've just seen, is stronger for weaker bonds. So in this case, for a strong bond, we expect HF to be the weakest of these three acids because we need the most energy to be able to break this bond. On the other hand, the HBr has the weakest of the three bonds, so we expect it to be the strongest acid. Similarly, we expect the strength of HCl to be intermediate. Now, let's keep in mind that this is all relative because many of you will know HCl is hydrochloric acid. That's a strong acid. So it's a weaker acid than HBr, but it's still, in absolute terms, a very strong acid, meaning that it's almost completely dissociated or completely dissociated in an aqueous solution. So in this context, strong and weak is relative, but all of these are actually strong acids. But even among strong acids, we can have trends in the strength of the acidity. Let's take a look at the second feature of bonding, which we know contributes to the acidity of a species, and that is bond polarity. Before we look at how bond polarity is linked to acidity, I'd like to remind you of what bond polarity is and how it's connected back to the feature of atoms that we call electronegativity. So remember that electronegativity is this property of holding electrons close to a particular atom. And this periodic table that I'm showing you here below lists below each atomic symbol the electronegativity for that atom. So here below hydrogen, you see the electronegativity of hydrogen on the Pauling scale, which is the one shown on this periodic table, is 2.2. Similarly, if we look over here at fluorine, its electronegativity on the Pauling scale is 3.98. And what those numbers mean is that fluorine, with a higher electronegativity, has a stronger tendency to hold electrons tightly than hydrogen does. How does that manifest itself when those two elements bond with each other? And let's just take HF as an example. So in the case of bonding between two elements that have different electronegativity, the electrons will be polarized. The electrons are polarized in bonds between elements of different electronegativity. And that's why we call those polar bonds. Now, a higher electronegativity means a higher tendency to hold on to electrons. In the case of H and F, fluorine has the higher electronegativity, meaning that fluorine is the element pulling the electrons closer. And we can represent that using these sorts of arrows where the positive side of the arrow is on the side of the bond that's more positive. So because the fluorine is pulling those electrons closer to it, the fluorine develops a partial negative charge in this bond, and the hydrogen develops a partial positive charge. You'll remember this lowercase delta represents partial. So this abbreviation at the top means partial positive and partial negative. So you can see all of these kinds of nomenclature used to depict polar bonds, either partial charges indicated or this arrow indicating the polarity of the bond. Now, how can you predict whether a bond will be polar or not? You're not going to sit down and memorize all the electronegativities on the periodic table. So instead, we need to remember the periodic trends in electronegativity. So you remember that electronegativity increases from left to right across the same period in the periodic table. And you remember that it decreases from the top to the bottom in the same group in the periodic table. So the electronegativity is lowest at the bottom of the periodic table, highest at the top of the periodic table. It basically follows the same trends that you see for things like ionic radius. So let's summarize those periodic trends in electronegativity. Electronegativity increases from left to right in a period. Electronegativity decreases from top to bottom in the same group. So once you know those trends, all you have to do is remember that the polarity of the bond depends on the electronegativity difference. Electrons will be pulled more closely to the more electronegative atom. Electrons move towards more electronegative atom. And we saw that already in our HF example. So let's come back to HF. In HF, we want to use electronegativity and bond polarity to decide which side of the molecule is positive. So we've seen already that the electronegativity of fluorine is higher than that of hydrogen, so that the hydrogen side is the more positive side of this molecule. So this is already giving us a hint as to how we should think about how bond polarity affects acidity. When we just draw a resting HF molecule, we know that it already has a partial positive charge on hydrogen, meaning it's primed to go ahead and create a proton species. The electrons are already spending more time near the fluorine than they are near the hydrogen, meaning it's not actually that difficult to generate a proton. So in general, for larger differences in electronegativity, i.e. more polar bonds, the species is more acidic. There is a caveat to that, which I'm going to show you in the next problem. So let's go ahead and take a look at this last problem. Which of the following bonds do you expect to be acidic or not acidic based on the electronegativities of the substituent atoms? Now, in order to do that, we need to know the electronegativities of each of these atoms. So I'm just going to tell you what they were from the chart up above. You can flip back in your notes and confirm that I'm not lying to you. Hydrogen was 2.20, bromine was 2.96, lithium is 0.98, and carbon is 2.55. So let's now look at each of these species. H and Br, hydrogen and bromine. There's a noticeable electronegativity difference between the two of them, about 0.7, with the preference for the electrons being towards the bromine, so generating a partial positive charge on the hydrogen. So we expect this molecule to be acidic. Now let's look at H lithium. In this case, the hydrogen is the more electronegative element. So you have to be careful here. This bond dipole actually points towards the hydrogen, and the partial positive charge in this molecule is actually on the lithium, meaning that this is not an acidic species. It's going to be extremely difficult to generate an H plus atom or an H plus ion from this particular species. Instead, get our pencil back here. This hydrogen is not referred to as acidic. Instead, we call it hydridic, because it's actually got a partial negative charge on it, it's going to tend to want to pull both electrons towards it to make an H- species, which we call hydride. Our last bond that we want to consider is the HCl, I'm lying to you again, is the HC bond. The electronegativities of hydrogen and carbon only differ by about 0.3. That's very similar, so that we don't typically think of this as a polar bond. So this is not an acidic species. Instead, the sharing between hydrogen and carbon is actually relatively even, and that turns out to be foundational in understanding organic chemistry. So in the previous unit, you learned about hydrocarbon fuels. Those are fuels that aren't particularly reactive towards acid or base chemistry because of the lack of polarity of this HC bond. So in this lesson, we've learned that both bond strength and bond polarity work together to determine whether or not a compound will be acidic. So whenever you're looking at a new molecule, a new compound, you need to consider both the strength of the bonds to hydrogen as well as the polarity of those bonds to be able to predict whether or not you're looking at a compound that will undergo Bronsted acid-based type of activity.